The lab activity this week is related to net force direction. For a couple of weeks, we've been talking about how we can determine the direction of the acceleration, and we've been doing this thing where, excuse me, an object is moving along a path like this. And let's say that we know that it's slowing down. Well, what can we say about the acceleration at this point? And the way that we analyze that is first, the velocity vector is tangent to the path in the direction of motion. And then because it's slowing down, we know that the parallel part of the acceleration, the part that's parallel to the velocity, is opposite the velocity. Now, as the object goes forward in time, we can see that it's on the, sort of left side, sort of the upper left side of the velocity vector line. And so the perpendicular part of the acceleration in this case is this way. And then based on that, we know that the total acceleration has to fall somewhere in this range of directions. So we've been doing that for a while. Well, now we're going to extend this analysis to the net force, because Newton's second law says F net is equal to the object's mass times its acceleration. And remember what happens if you multiply a vector times a positive number. It doesn't change the direction at all. And so what that means is, under any circumstances, all the time, if you know the direction of the acceleration, that's also the direction of the net force. In this class, we don't think about net force too much. We tend to think about the individual forces that make up the net force. But we can analyze the direction of the net force this way. And so in this lab activity, you're just going to go this one step further in thinking about directions. And so in the example above, where this object was traveling along this path and slowing down, we figured out the range of possible directions for the acceleration. And what that means is that range of directions is also the range of possible directions for the net force. We know that the net force, if you add up all the forces, you'll get a vector that falls in that range of directions. And so in this activity, you'll do a few, there are a few motions that are along a line. And remember that if something isn't turning, then it doesn't have any perpendicular acceleration. And so you'll do a few like that. And then you'll do a few circular motion problems. The first one is like a tetherball problem, where this object is moving around a circular path like this. Okay, and remember that if something is in a tetherball problem, we're always in circular motion. So there's no parallel part of the acceleration at all, because the speed isn't changing. And so in this case, if you're looking at this path from above, and say this object is going this way, then at this point, the velocity vector is this way. There's no parallel part because the speed isn't changing. The perpendicular part of the acceleration is this way, and since there's no parallel part, that's also the total acceleration direction. And since we know the direction of the acceleration, we also know the direction of the net force. And it asks you to show those vectors in two different planes. So I did it in one plane, but it asks you to do it in another one also. And then we go to one where this ball, it's like a tetherball problem, but instead of spinning horizontally, this ball is swinging around a circle this way. So the height is changing as it swings around. And when a ball is doing this, it's at its fastest when it's at the lowest point, and it's at the slowest when it's at the highest point. And anytime it's changing height, if the height is increasing, it's slowing down, and if the height is decreasing, it's speeding up. Well, okay, so what you need to be aware of here, if this is the circular path, is that there are 2 points on this path where the ball's height is not changing, at the top and bottom. At the top and bottom of the motion, instantaneously the height isn't changing, and so there's no speed change at those two instants. And so at those two instants, and those two instants only, there's not going to be any parallel part of the acceleration, only perpendicular. And so it asks you to do that analysis also. And that's really all there is to this lab. So let's, on this one, let me show you, let me do an example. So let's say that we're looking at this point here. What can we say about the direction of the acceleration and the net force here? Well, the velocity is tangent to the path, so this way. At this instant, the ball is rising, its height is increasing, so there's a parallel part of the acceleration that's this way. It's turning this way, so the perpendicular part is toward the center. And so the total acceleration is somewhere in this range. And since you know that the direction of the acceleration is in this range, you also know that if you added up all of the individual forces to get the net force would also fall in that range of directions. Okay, that's all.